Okay, to start off with, I want to make sure that some notation is understood. So if you have the sine squared of x, understand that that can be written as the sine of x quantity squared. If you have the tangent of x squared, that is understand to be inside here, where this is the argument of the trig function, and over here this is the argument x of the trig function. All right, so let's go ahead and look at that first example that I have. And the first example that I want to use with this today is if I have the tangent squared of theta. Now, we can actually do this two different ways. The first way is going to be with the chain rule. And again, remember that this means that this is the tangent of theta quantity squared. So using the chain rule, the inside portion is going to be the tangent of theta. We're going to go ahead and let u equal tangent of theta. The derivative of the tangent of theta is just the secant squared of theta. All right, so let's go over here again. That means the derivative of u is going to be 2. The argument on the inside, that u always stays as u, to the first power. And then I multiply this times the derivative of u. So you then have the first derivative is equal to 2 tangent of theta times the secant squared of theta. Now, what's the other way we can go through and prove this? Well, could you also show using the product rule? And yes, we can, because this way we say y is equal to the tangent of theta times the tangent of theta. So in this case, our first u is going to be the tangent of theta. The derivative of that is the secant squared of theta. Then I have v, which is my second tangent of theta. U prime is going to be my secant squared of theta. So using the product rule, I can go ahead and say that the first derivative is equal to the tangent of theta times the secant squared of theta. So that's just the tangent of theta times my secant squared of theta plus the secant is squared times the tangent, and I'm just going to write them in the same order. It doesn't matter the order you write them in. So this is again the tangent of theta times the secant squared of theta. And just as like if I had a plus a anywhere, you would have 2a. I have one of these. I have another tangent, so that tells me this is equal to 2 of the tangent theta times the secant squared of theta. All right, so let's go ahead and try this one. Again, remember, whenever you have the exponent around the cosine or any trig function, you can go ahead and rewrite that. And what this really means is that you have the cosine of 3x quantity squared. So this is a case of being able to rewrite this as y is equal to u squared when you can let u equal the cosine of 3x. So what is the derivative with respect to u? That just becomes 2u times u prime? Well, let's find u prime. U prime is equal to, now look what we have here. I also, again, have another u inside here. This is an example of the double use of the chain rule. So what you're doing here is you take the derivative of the cosine, which is minus the sine of 3x. Again, the inside stays the same. Now I take and multiply that times the derivative of that argument, which in this case, again, is times 3. So what is y prime? I substitute back in for u and u prime. I get 2 times u, which is the cosine of 3x, times u prime, which is, I'm going to rewrite that in the order, put the negative 3 first, and make it that negative 3 sine of 3x, which gives me negative 6 cosine of 3x times the sine of 3x. All right, so we're going to do this again. We want to find the first derivative, and this is again taking the form of f of theta is equal to, I'm going to rewrite that square root and change it into the 1/2 power. Now, this actually brings up something that's really interesting with this. My u is the inside portion. But if I look at u is equal to the tangent of 5 theta, which means inside this, I actually have another u. When I take the derivative of u, the derivative of the tangent of 5 theta is the secant squared of 5 theta, but I have to multiply that times the derivative of the inside. I have to multiply that times 5. So with trig, a common saying when you're doing this is just keep chaining and using the chain rule until you can't anymore. Now for ease of writing this, I'm going to rewrite this as 5 of the secant squared of 5 theta. So let's take the derivative of the outside of my function. So the derivative with respect to theta is equal to 1/2. The inside portion, where what I let u is, stays the same. This becomes to the negative 1/2, and I multiply that times my u prime, or f prime of theta is equal to, I'm going to turn this into a fraction. This is to the negative 1/2, so it's going to go in the denominator. So I'm going to write this as u prime all over 2 tangent of 5 theta. And now finally I'll rewrite the whole thing as 5 secant squared of 5 theta all over 2 tangent of 5 theta. All right, so with this one, I'm going to try to put it all together. So let's go through and find the first derivative. Before I do that, I'm just going to make sure I rewrite this one more time. I can't emphasize this enough. I'm going to rewrite this as the cotangent of pi x plus 2 quantity squared. All right, so what does the chain rule tell me to do? The first thing I want to do is take the chain of the outside. What that means is h prime of x is equal to 2 times 2. Everything that is on the inside here stays the same. We don't change any of this right now. So that stays as the cotangent of pi x plus 2. And this now becomes to the first power because that is just 2 minus 1, so that gives me my 1. Now, what the next part is now I have to take the derivative of the inside. To take the derivative of the inside, I need to take the derivative of the cotangent, which is minus the cosecant squared. But again, I have another inside piece. The inside part stays the same, which leaves me with pi x plus 2. But again, one more time, I've got to take and multiply this times a derivative of what is inside that. In this case, pi is treating it as a constant, so it's just going to be pi. So we are all left with h prime of x is equal to negative 4 pi. I'm getting the negative 4. It's 2 times a negative times a pi. Remember, all of this is being multiplied together, so I'm just pulling the non-trig functions together. Then what am I left with? I'm left with the cotangent of pi x plus 2 times the cosecant squared of pi x plus 2. And I can leave it like that, or I can turn it back into the sine and the cosine of those functions. If I do it and turn it back into there, that becomes h prime of x. Remember, the cotangent is just the cosine over the sine, so that becomes minus 4 pi of the cosine of pi x plus 2 all over the sine of pi x plus 2 times 1 over the sine of pi x plus 2, all leaving you with negative 4 cosine of pi x plus 2 all over the sine of pi x plus 2. So I just want to go back to the beginning and show you why it's so important with what we're doing. So you take the derivative of the outside, then we took the derivative of the inside, but again, I had another function inside of a function, so then I took the derivative of that again. You're going to see that often when you're dealing with trig functions.